Specs in SSD, and speaker is uh, Dr. V Kalyan, with the main organizer of this FDP. So let me quickly introduce Dr. Kalyan. So he's an assistant professor at the Department of CSC, IIT Ropar. And prior to joining this IIT Ropar, Kalyan was a hardware performance architect in System and Technology Group Laboratory, IBM Systems, Bengaluru. Kalyan received his PhD under the guidance of Professor Madhumittam from Department of CSE IIT Madras. And currently, his research interest is computer architecture, mainly memory hierarchy and low power energy efficient techniques. Thank you, Dr. Kalyan, and now over to you.
Okay, thank you, Dr. Srishandu. So I understand this is the last session after the long week that has been going. This is the fifth day of this FDP, and there were a lot of interesting lectures, and many of them were quite intense. What I thought was to keep this particular session little light. I'm going to give more of an overview of the storage architecture and the possible issues in them, right? So with that, I'll start my screen sharing. I'll switch off my video for bandwidth sake. Let me share my screen. I hope you are able to see my screen.
Yes, it's visible.
Okay. Okay, I've made it full screen. Is it showing up?
No, full screen is not showing.
Okay, stop sharing then. Let me check. How do I do it?
You share the entire screen, then I think.
Okay, let me try that. Okay. Does it show now?
Yes.
Let me try full screen.
Yes.
Okay, great. Okay. So this session is titled Security Aspects in SSD. SSD stands for solid state drives. We are going to start with very fundamental aspects of the storage, and we are going to build further to the sophisticated storage that we have currently, right? With that, let me begin. This is the quick outline of my session. So for the first few minutes, I'm going to put the notion of security in perspective on what led to such a situation that we have to think about security, right? Some of this is already touched upon the previous sessions. So following that, we will have a short session on the SSD storage architecture itself. It has two subtopics, which is the basics of the NAND flash, and followed by the workings of the SSD controller, right? And the third subpart of this session would be the security aspects in storage with the knowledge of the underlying storage architecture. In that, we are going to look at a few threat models and a couple of specific issues or attacks, we can say, namely secure deletion and ransomware attack. So to begin with, the very basic stuff is the popular notion of three walls of computer architecture, right? And the reason why I brought this up is that the modern computer architecture that we study, or the one which is implemented in almost all the chips that are available to us, is heavily influenced by these walls, right? And majority of the designs that we see today both designs, optimizations, etc., are basically trying to address these walls and trying to give a product which has decent quality of service. Right, the three walls are named power wall, instruction level parallelism ILP wall, and the memory wall. So a few speakers have touched upon these walls already, but I thought it would be good to stress them a little more, right, and drive to the point where the security is coming into picture. So let's start with power. So the power typically has two major components: dynamic power and static power. Dynamic power is given by the capacity load that is switching and the voltage that is supplied to the circuit and the frequency of operation. So we can, in short, we can say C V square F, right? And dynamic power is the power that is consumed when the transistor is switching, and when does the transistor switch is based on the operation that it is trying to be part of. So dynamic power is usually considered as useful power, meaning that this power is spent doing the work that we assign the circuit or the processor to do. Right. On the other hand, we have something called static power, which is basically needed to keep the circuit on. So a quick example here is we have our mobile phones, and let's say we charge it full at the beginning of the day, and throughout the day we will not use them. Of course, highly unlikely, but yeah, if that is the situation, the battery drains out by 10-15% easily. So that part is the static power, because just to keep the phone in the standby mode itself, we need to power on a lot of internal circuits. And in general, the static power is proportional to the number of transistors that are switched on at any given moment. So at the beginning of a few decades back, when the notion of integrated circuits has come into the picture, the number of transistors were few, so the static power was quite less. And in the static power, the leakage power is the major contributor. Now let's look at the dynamics of these both components, right? So here is a picture, a graph basically, where different lines are plotted for different technology nodes, starting from 180 nanometer to 70 nanometer. And on the x-axis, we have temperature, and y-axis, we have the ratio of the static power to the dynamic power. So we can clearly observe that with the shrinking of the technology, right, the fraction of the fraction that is contributed by static power is increasing. Also, with the temperature, the static power component is increasing, because leakage power is dependent on the temperature, and as temperature increases, the leakage power will increase. So, excuse me. With this point in mind, we can say that we should not be overlooking the static power dissipation in a chip. If we overlook, what will happen is the chip will get heated up and burn out. Now, so one of the very first law that was or statement we can say was done by or proposed by Gordon Murray, the co-founder of Intel, and that's what we call Moore's law. At the same time, we have another such a statement by Dennard. We call that Dennard scaling. It also has goes in the similar line, saying that for every generation, the number of transistors will double, the frequency will be up by 40%. And also he made an important statement that the power consumption of this scaled chip will more or less remain same. What it basically means is the power burnt in by the chip before and after will be same. And if we bring in the physical area into the picture, we call that power density, right? So this was the Dennett scaling, and uh, one of the things that happened was, with this Dennett scaling in mind, the manufacturers planned their cooling capacity for a given chip. So what it implies is, if I have built a cooling system, whether it can be liquid cooled or even a simple fan based thing, that would still remain same across different generations. But that was not the case, because Dennett assumed that only the voltage is the one which is scaling. So if you remember the dynamic power, CV square F, with technology, the V will reduce. So we'll have likely double the reduction in the power. But now, because we have double the transistors, overall the power might remain same. But Dennett's mistake was he overlooked leakage. In the previous slide, I showed that static power component is increasing, and in that leakage power is also increasing. So what happened was Dennett scaling has failed. What it implies is we cannot switch faster, or we cannot keep all the transistors, even though we have a billion of them in the current chip. We cannot switch them on at the same time, because the leakage, because of the leakage power, the chip will get heated up. So this is popularly called as power wall. And at the time when the power wall concept was brought in, so there were popular studies that were doing. On the right side, you can see that on the heat sink of the processor, there, somebody was making an omelette. So there were some similar enthusiasts who were baking noodles on top of the heat sink. With this point in mind, what happened was the dynamic power component was put in place by limiting the frequency. In CV square F, though voltage is reducing, now we are also limiting the frequency so that the dynamic power consumption will more or less remain in the same ballpark. So here there is a figure on the right side which shows the power consumption of various Intel processors right from 1982 to 2012, and it has two lines. The black line is for power, the blue line is for clock rate. So till 2004, where the Intel Pentium 4 came up, so both were more or less increasing, but nobody noticed on the power much, and they were happy shrinking the transistors and increasing the power. But later on, at this point, when they realized that the power dissipation was too much, they have tapered down the frequency. So we don't see any increase in the frequency, and also it has only supported by some other different processes. It has been slowly increasing. So the immediate effect was seen on the power consumption here. In addition, we have some new techniques called dynamic voltage and frequency scaling, which will try to adapt to the workload that is being run on the chip. And I have also included one other graph on the lower right corner. On the x-axis, we have the load that is on the processor, and on the y-axis we have the on the different lines stand for different frequencies, and on the y-axis we have the power consumption, right? And this is a demonstration of how DVFS would give the benefit. So when based on the load, when we try to scale the frequency from 2.4 to 1.8 to 1 gigahertz, we have some savings in the power. So at the same time, we had the notion of low power modes, and this overall brought up the power aware designs into the picture. No longer power was a free lunch. Accordingly, we had clock gating and frequency gating we have already seen, logic gating also. On the static power front, the only way was not to switch on all the transistors, and because of this, some portion of the chip was always in the off mode. That's where the notion of dark silicon has come. Moving on to the ILP wall, as you are aware that we can execute multiple instructions in parallel, and because we had multiple functional units and we can overlap, so that was resulting in higher and higher performance. We were chasing it till the 2004 time frame. Again, it is overlapping with the power wall issue that has come, right? So nearly for 2.5 to 3 decades, we were experiencing 52% of performance increment with every generation. But after that, it has tapered off. It has a link with the power aspect, but also on the performance aspect. What happened was till 2003-2004 time frame, we started from a simple scalar in order, we moved to scalar, a superscalar out of order, then a very deep superscalars with nearly 25 plus stages, right? And following that, we have deployed speculation and multi-threading, and overall a big complex superscalar was deployed. And the classic example for that is the Pentium 4, right? But because we were not able to continue the cooling aspect, we had to drop such complex circuitry. In addition, one other problem was the prohibitive speculation cost, because the more and more number of instructions that we are trying to execute in parallel, the more penalty we would pay if the speculation goes wrong. So it was also that the number of just by increasing the pipeline stages, the performance was not improving. This, you can call it as the law of diminishing returns, right? All this contributed to a kind of gap in the performance that we expect and the performance we get. So just because we have more and more transistors with technology scaling, it was not translating into higher performance. So how did we handle this ILP wall is to understand it, we cannot switch on all the transistors because of the power, nor we can deploy a single superscalar because it was no longer giving good performance, either because of speculation or because of the diminishing returns. So this led to two major options on how to use the additional transistors that were being provided with technology scaling. One is that we should increase the number of cores on a single chip. And what it led to was a direct impact on the software development. So till 2004 time frame, the software engineers and the hardware engineers were happy with their own work. The software engineers used to assume that they will get a better hardware every year. And the hardware engineers used to assume that they would be able to support any type of workloads. But with the move from single core to multi-core, improved coordination was needed. In addition, the increased number of transistors were devoted to the cache, on-chip caches to exploit the existing locality. It was only beneficial to a certain extent. We are going to see that in the memory wall issue. So this move from the unicore to multi-core was primarily driven by the slowdown of Moore's law, then the ILP wall, and of course the power wall. So there was a popular notion in 2004-2005 time where people used to say, the engineers used to say that instead of deploying a single horse, we are going to deploy hundreds of rabbits to do the same work, right? Moving on to the third wall, which is memory wall, it's already established in the previous lectures that the DRAM capacity and the speed were not proportional to the processor computing capability or the speed, right? The processor was performance was increasing nearly 50%, 60% a year, but DRAM performance was increasing only 7% in a year. So with time, the DRAM was becoming slower and slower. So to handle this, which is termed as the memory wall, right, to meet the latency or the speed of the CPU so that the latency of memory is not in the critical path, the caches were proposed, right? Multi-level caches were deployed after that. And we now have multi-levels of main memory also, followed by multi-levels of secondary memory also. And all this was primarily based on the notion that the applications tend to have locality in their working, or when we execute an application, majority of the time the application is going to use a limited or the hot data more than the remaining data. And if we keep this hot data nearby, we have solved the the memory wall problem. That was the primary motivator. But did we actually solve the memory wall? It was addressed to some extent, but it has resurfaced when we moved from single core to multi-core. As you can understand, in the beginning, we were expected to support the requests, the read-write requests from a single core. But now, if we have 4 core, 18 core, or 16 core trying to access the data from the memory, we need to scale accordingly. So this has put an increased pressure on the caches and the main memory. Caches were experiencing more interference from the cores, right, leading to increased accesses trying to go to the memory. And also coherency issues were cropping up. And like I mentioned earlier, trying to serve all the requests in parallel to different cores is a big task, which is actually pushing the capability of the memory to supply multiple data items at the same time, which we generally call as bandwidth. So this was one one side of the story where the hardware move from single core to multi-core was pushing the memory wall. On the other front, the applications that were being developed were more and more yeah, I'm trying to reconnect now. Am I up? Okay.
Yes, you are audible now.
But is my screen visible?
Yes, screen visible.
Okay, just 1 second. Okay, so let me go back to my screen.
Yes.
Okay.
Yeah.
Thank you. So the nature of applications has changed. They were exhibiting less and less locality. So the caches were of not much help here. Again, the memory was in the critical path. Also, the applications were getting bigger and bigger. Because of this, the entire application was, the working set at least, was not fitting in the caches. In addition, because we have multiple cores and multiple applications running simultaneously, the interactions between the cores and interaction of these applications with the caches and memory were leading or demanding more bandwidth. So that's where the modern memory wall can be said to have happened, where both the memory latency and the bandwidth are critical. So what happened with this modern memory wall was the architects started exploring new mechanisms on how to adapt to the changes in the application, right? So the cache and main memory policies were becoming more and more adaptive. So the cache sharing, you can say, or the replacement policies, right? Everything were trying to learn from the application that they are running and adapt to it. In addition, there was a tangential exploration wherein the data and the memory are no longer away from each other. Rather, the computation is performed in the memory or very near to the memory. So this brought in the near memory computing paradigm, right? And this can be explored either at the main memory level or even at the secondary memory level. The third option was to bring the memory closer to the processing unit. So there we had 3D stacking of many DRAM layers. So this was explored by two major products. One was hybrid memory cubes and other was high bandwidth memories. So because of 3D stacking, right? So the DRAM layers were not only close, they were also one on top of another, leading to more power issues, right? Now, all these were, like I said, over the past few decades, were the driving factors for the modern architecture that we saw. But currently, I took the liberty of calling the current status as the fourth wall, which is the security wall. Why? Because everything needs to be security aware. So a few examples to show why we are thinking about it, right? Is our data so vulnerable that we need to think about security all the time? Is the situation of the hardware so dire that we will not be able to use it the way we used to, right? So to quickly correlate to this situation, a few examples from our day-to-day life. I think this is the current status of each and everyone, that we think twice before we use any public network, either when we are in the airports during transit or in the malls, right? We don't straight away connect to any available Wi-Fi network or any hotspot, because we are scared that some data or some logging of our activities can take place, right? And then we think twice before we download any app. Even though we are interested in its utility, we still go and check the developer details. We go and look at the ratings of the other users, etc., to get some basic level of trust. And even when we install, we try to think consciously on which permissions it needs, etc. And when we are making an online payment, and whether it's any shopping or even simple internet banking, we check the link twice, whether it is a secured link or not, right? And even when we are checking our emails, we think twice to click any links that are part of the emails. We first try to gain some confidence that it is from a trusted sender, only then we are going to open it, right? Otherwise, we have a lot of cases of Trojans and malwares, right? And now this another example that you can correlate is creating a password has become a big issue now, right? So gone are the days where the password was simply our name extended by date of birth or something like that. But now the minimum expectation is the password should contain at least one capital letter, one special character, one numerical, etc., etc., and with minimum length of 8, so on and so forth. And On top of it, we are expected to change it for every 3 months or 6 months. And another easy example that you can correlate with is when we are entering the pin at the ATM, we try to cover it with our hands. We are more conscious about the over-the-shoulder viewers also, and the anybody watching from the CC cameras trying to figure out the password or the pin, right? Also, you would have heard about the new devices that were being plugged into the ATM machine so that they can track your pin. Right? We check these things whenever we go to the ATM, whenever we want to withdraw or do some transaction there. Also, when we are giving our device to anybody, we think twice. It's not like that we are giving our pen for them to use. Right? All these are there. And in addition, when we are trying to purchase any device, any computing device, we also look at the country of origin. Now, you would have realized that there is a push from Government of India that is discouraging us from purchasing either hardware or software from our neighbor. You can guess the name. So all these issues are there. We have adapted to such demands. And the point I'm trying to stress is security issues were always there. Now, why it has become more and more relevant is because of the increased global connectivity that we have, increased speeds, right? Increased capacity of the connected devices, and the hardware earlier was a private resource, but now it has become a shared resource. So if you want any compute intensive application, we don't run on our laptops. Rather, we try to run it on a remote server. It can be AWS or anything like that. And even if you think about the notion of Chromebook, right? Even our simple every bit of data is stored in a cloud, right? So it can be viewed as a cloud, or it can be viewed as an SoC where different types of chips are embedded into, right? So these chips can have different manufacturers, and again, the trust issues will come. That's where the notion of hardware trojans are coming into picture, where we do not have the basic trust on one or more of those chips. We are suspecting a foul play. Right, and within a multi-core processor, we can assume that there might be a aggressive application, right? An adversary who is trying to just slow down the system, right? It can be the simplest way to affect the victim, or it can try to steal data. That's why we have many side channel and core channel attacks now, right? And within the same core, we have this notion of multi-threaded execution, right? So even our private L1 caches are no longer safe, and we have some threats because of that. So our design choices that we made to address the previous walls have led to the current situation. But does it mean that our approach was wrong, etc.? Probably not. But we still need to understand that security is need of the hour. So security aware designs are needed, and that's the reason I have labeled it as the fourth wall. Earlier we had power aware designs, performance driven designs, and memory aware designs. Now we need to put them all in the as a subset of the security aware designs, whatever we are going to build, right? So in addition, I have put the last point here as technology scaling, because with the technology scaling, the transistors are becoming smaller and smaller, and they are becoming more and more susceptible to the disturbances around them. So for example, the row hammer attack that we are discussing, right? It would not have been possible if the technology node was around, let's say, 180 nanometer. Even if it were there, the effect would have been very minimal. But with scaling of the memory, we see more and more such disturbances, and we need to equip our hardware accordingly. So with this point or motivation in mind, in this session, we are going to look at the possible security issues that can happen in storage, right? Again, all these issues I'm going to put in three aspects, right? This you have heard time and again, the CIA problems, right? Confidentiality, that only the authorized user should be able to access the data. Integrity, where any change in the data needs to be traced out or should be traceable. It should not be possible in the first place, but if at all some change is there, we should be able to trace it back. And the last point is the availability, that the authorized user should always be able to access his data. So with that, let's dive into the storage. So I'll pause for a minute for any questions. Okay. So let's move on then, because I have covered, rather reiterated all the previous sessions. I'm taking confidence that you do not have any questions now, right? So let's dive into the secondary memory. So a quick point about why we should be concerned about storage to begin with. So on the screen, you can see a term internet minute. So it is defined as all the activities that are happening over the internet across the globe. Okay, and there is a popular site which is called Domo, in short, right, that releases studies that it has performed every year. So current iteration is the 9th one, and it labels these studies very interestingly, that data never sleeps, right? Now, this particular organization was trying to track all the activities that were happening in a 60-second time window. Now, here in this picture, you can see all the various activities that are happening. For example, on Twitter, roughly there are 575,000 of tweets. On Instagram, there are 65,000 photos that are being pasted. On Facebook, around 240K photos are posted, etc., right? On YouTube, so many hours are being viewed, and because of the online push, because due to the pandemic, we have more and more on the Teams and Zoom, etc., right? Now, all this is, like I said, was in the global connectivity has increased. So the overall internet users across the planet are now 5.2 billion, and every activity that they do generates the data, right? Now, to support such huge data that is generated, right, organizations need to be equipped with efficient storage systems. A few more examples of the data and the amounts of data that is being currently looked at. Facebook study reveals that every day 4 petabytes of data is being generated, right? This was in 2015-2016 time. Now you can assume that it might be 1.5 to 1.8 times easily, right? And Google was handling sorting problems on 50 petabytes of data, right? And again, this was sometime a while back. You can assume that it would have been 2 to 3-fold now. So because of the increased connectivity, the notion of big data has resulted in such huge amounts of data and the applications that want to use this data, right? And because of this drive, almost all the major chip manufacturing companies provide storage solutions also. We primarily see Intel to be a processor manufacturing company, but if you look at other products, they also support, they also come up with Intel Optane memories, etc. Right? So when we look at the secondary memory, we cannot go with the standard SRAM and DRAM based implementations because they are very costly, and they would burn a lot more power, and also they are volatile in nature, meaning that if you turn off, they are going to lose the data, and we do not want to lose the complete data when we want to shut down our system, right? And accordingly, we have various non-volatile memories. A quick walk in history lane, I should say, right? We started with magnetic disks, which would look something like this, and magnetic tapes. So earlier the tapes were very huge, but now we have some not now, it's been like at least 20 years that we have some miniaturized version of these magnetic tapes. Then there was a notion of floppy disks. Then after that we had optical disks, right? We had various versions, CDs, DVDs, Blu-ray, etc., with increasing capacity and increased usability. Right. The most recent one is the flash technology, and that's what this session would be concentrating on. Right. The reasons for moving to the flash technology. A quick tabular form here. When compared to the hard disks, right, which are based on magnetic polarity, SSDs are based on the flash cells. The random read latency, as you can see, is at least 10 times faster. The power that is consumed by HDD and SSD is 1/3 of the power consumed by the HDD, right? The noise, there is no noise with the SSDs, and but still the HDDs are cheaper, but the cost of SSDs is coming low thanks to the technology scaling. On reliability front, SSDs have low reliability, and HDDs have low reliability and SSDs have high. And lifespan, it's surprising to note that our HDDs are having high lifespan when compared to SSDs. Weight, typically the SSDs are lighter. And what type of workloads we need to look at to decide on HDD and SSD is HDDs are very good for large workloads which have sequential input-output operations, and SSDs are good for small random input-output operations. Right? SSDs are primarily based on flash memory technology. So again, a quick walk through the memory lane. It all started with the read-only memory, which got extended to programmable read-only memory, and then erasable programmable read-only memory. Following that, we have EEPROM, which is electrically erasable programmable read-only memory. And what we have, the current flash memory, is an evolution from the EEPROMs. And here, the granularity at which we can write to a flash memory is an entire block. We are going to see what block is and the ramifications of such a granularity in our upcoming slides. Right? The flash memory cell, the key element is the floating gate metal oxide semiconductor field effect transistor, MOSFET to be in short. So if we consider an NPN transistor, so don't worry, I'm not going to get into the device level details. I'm just going to skim through the operational aspects of it. We have one terminal as source, another as drain, and there used to be a oxide layer, insulation layer, and on top of it we have a metal layer which is termed as gate. Now in floating gate MOSFET, instead of directly connecting the metal layer to the gate, or the oxide layer to the gate, we have another semiconductor in between, which is called floating gate, right? And to which that is connected to the gate terminal. Whenever high voltage is applied at the gate, the electrons move from the channel to the floating gate. They get attracted, and this is called tunneling. Right? Because of tunneling, what gets impacted is the threshold voltage of this transistor itself. If there was no tunneling, the threshold voltage would be the standard one. But because of tunneling, the electrons that get trapped in the floating gate, the threshold voltage tends to be higher. Right? If when we are given a floating gate MOSFET and we apply the standard threshold, if we see that still the current is not flowing from the between the source and drain, we would realize that there are some electrons trapped in the floating gate, and we term it as storing a 0. But if there is a current flow between the source and drain, we call it as 1. And the best part with flash cell is it's non-volatile, meaning that even when the source, gate and drain terminals are not connected to any power source, the electrons that are trapped in the floating gate remain there. Right? And now a quick overview of the working. How do we read the data that is stored in the flash memory is we apply the threshold voltage and observe the current. If there is no current, then we term it as 0. If there is current flow between the source and drain, we term it as a 1. And how do we write a new value to the flash memory cell is we apply a very high voltage to the gate, and the electrons get trapped into the at the floating gate. And as mentioned earlier, this is termed as 0. Now, how do we erase the flash memory cell? Is again, we apply a very high voltage at the gate terminal, but with opposite polarity that will repel all the electrons, and the floating gate is ready to be programmed again. Programming is same as writing to the flash memory cell. And erasure can be equally termed as writing a 1. And the flash memory cell has this very specific requirement that we need to erase it before we can write a new value. So this the tunneling that happens through the metal oxide, right, leads to a lot of stress in it, and because of this, there is eventually the metal oxide breaks, meaning that the transistors will no longer be able to be trapped. So this process is in general called as endurance, meaning the number of times we can write or erase a flash cell. And flash memory cell typically has very limited endurance. This was not the case when we consider the SRAM, DRAM, or even the magnetic disks. Okay, what we have seen is storing 1 bit of information, but based on the number of electrons that get trapped in the floating gate, we can make more interpretations. Accordingly, we have single level cell, wherein when we apply a single threshold voltage, if there is current flow, we term it as 1, otherwise 0. In multi-level cell, instead of 1 threshold voltage, we have 4 of them, VTH 0, 1, 2, and 3. Sorry for the typo. And for whatever threshold voltage we observe current, we would interpret that as 0, 0, 0, 1, 1, 0, or 1, 1. And the same concept has been extended to have a tri-level cell, wherein there are 8 possible threshold voltages, and we give each threshold voltage one at a time and see when the current flow is happening at the flash cell. So a pictorial representation of the same, I'm going to skip that. If you look at the speed of operation, the single level cell is much faster, because all we need to do is apply a single threshold level and observe the current. As we go deeper to MLC and TLC, we need to have multiple steps there. And if you look at the density and the cost of TLC is much lesser than MLC and SLC, and also the density is proportional to the number of bits you store. It is 3 times more denser than SLC. If you look at the endurance, it is again reverse, because we need to apply multiple threshold voltage even for a single read, right? It is going to further stress the metal oxide layer, so the endurance is less for the TLC when compared to SLC. Now with this single flash memory cell, whether it is storing 1 bit, 2 bit or 3 bit, whatever, let's try to make it zoom a little, zoom out and try to create an entire memory structure, right? There are 2 primary implementations of this. One is NOR flash, another is NAND flash, right? I'm going to skip the differences here. So here is a quick table on comparing the NOR and NAND flash, right? NAND flashes are more denser, their cost is less, but NOR flash is faster for read operations. NAND flash is faster for both write and erase operations, right? And in general, NAND flash is used for the data storage, and NOR flash is used for code storage and execution. And if you look at the cost, NOR flash is much more costlier, right? So in small embedded devices, we would typically go for NOR flash, but in all other devices, we would be looking for NAND flash. So now let's look at the 2D arrangement of such NAND flash cells, right? We have first a string of such NAND cells, which is one column here, meaning the source of one cell is connected to the drain of another cell, so on and so forth. Okay, and the gate terminals are forming the word line. And each string is of typically length 32 to 64 cells, right? And this is the minimum read granularity of a NAND flash. A 2D arrangement of such strings is an array, right? And a page is a row of cells in such array. And this is the these are the typical sizes of the pages, right? 4 kilobyte, 8 kilobyte, and 16 kilobyte. If we say each cell is storing 1 bit of information, then on the row we have so many cells lined up, right? And this page is the minimum size that we can write to. So here there is a disparity between the read granularity and the write granularity. This was never the case when we were looking at the SRAM and DRAM, right? So we can still read a single bit of information and write a single bit of information in SRAM and DRAM, but not so in SSD. So let's take these NAND arrays, and when we arrange such arrays in a 2-dimensional fashion, right, that will form a block. Typically, the block sizes are in few megabytes, and this is the minimum arrays granularity. So minimum read is size of a string, minimum write is size of a page, and minimum arrays is size of a block. And when such blocks are arranged one on top of another, stacked, that's what we call a block. Sorry, a plane. And when such plane are arranged in a 2D fashion like this, it would form what's called as a NAND die. And NAND chip is collection of such NAND dies, right? So what we typically see on our USBs and hard disks, the SSDs, would be these chips, right? NAND chips. And NAND chips internally are divided into die, plane, block, pages, arrays, and strings, right? And this is a picture from the Micron. This is how a typical NAND chip would look like. Now, such NAND chips can be again organized in a 2D fashion, right? And they can be called as channels and banks. Explain it here. So all the chips that are forming a single column here can be termed as a bank, and all the chips that are forming a single row here are called channels. So here in this figure we have 8 channels and 2 banks. And why do we need such an arrangement is the data transactions between channels can happen in parallel, but only from one bank. So the number of channels and banks will be based on the SSD that is being built eventually, right? Typically, the low-end SSDs will have 2 to 4 channels, but if you look at the high-end SSDs, typically there can be 10 channels. And the decision on these channels and banks is based upon the performance, the power, and overall size that can be adjusted or accommodated, right? So with that, we now come to the SSD architecture as a whole, right? This is a typical SSD that we have. If your laptop has a SSD, this would how it would look typically, right? Or an elongated version of this. And this is an external SSD. And if you open either of them, this is how the arrangement would be, the PCB, right? And here is a close-up of that. So each of these black boxes are the NAND chips that we were discussing till now. Okay, and there is another special chip that is the SSD controller, which will manage all the data in these NAND chips and also talk to the host interface. So with that, I'll take another small pause, right? I'm open for questions. What we have seen is the basic working of the NAND flash cells, right? And how they are arranged. And the important points that we need to take forward is that the NAND flash requires we need to erase it before we can write a new value, and also the read, write, and erase granularities are different. Any questions? Okay, I'm assuming that all of you are comfortable with the basics now, right? This is where we are. We are looking at the SSD controller now. Typically, the role of SSD controller, like I have mentioned, is to manage the communication between the host system, which can be our laptop or a desktop or even the processor on the mobile phone, right? And the NAND chips. It should support all the popular interfaces like SATA or parallel ATA or USB or PCIe, etc. Right? And the controller will try to be will have an interface with the host, and also it will manage the NAND chips. So let's dive into the SSD controller now. So there are various functionalities that a typical SSD controller needs to overlook, right? I've grouped them. The first one is reliability and maintenance features. The security features are the second, then the performance features, and the last are the remaining miscellaneous tasks that it performs. When it comes to the reliability and maintenance features, there are at least 10 different tasks that the SSD, controller is expected to look into, right? Starting from address mapping, where leveling, garbage collection, over provisioning, read and program disturb, write abort, ECC, correction, right? And SMART, we are going to look at it, and then the defect management and different RAID levels. On the security front, it has an encryption and decryption engine. On the performance front, it has a disk cache to manage, and the other miscellaneous tasks are the actual file layers, right? All these are handled by a specialized RISC processor that sits along with the NAND chips. And this is not an arrangement for any typical pen drive or so. This should be an internal or external storage device itself. Right? We'll start with each of them. We'll spend a few minutes and move on. The very first one is the address mapping. Right? It's called the flash translation layer. What it primarily does is converts the address that is given by the host, or for simplicity, you can assume that the main memory experienced a page fault and the OS has now contacted the storage with an address of one page, right? That address, we refer it to as logical block. That needs to be converted into the physical block address, PBA. And this flash translation layer has this mapping in it. It's basically a table. So the logical blocks can be in sequence 1, 2, 3, 4, 5, 6, but the physical blocks can be slightly different. Here, 1 is mapped to A, 2 is mapped to B, but 3 is mapped to E, and 6 is mapped to C, etc. Now, why is such a difference in the mapping? Why is it so non-linear, so to say, right? The main problem that the SSD controller needs to look at is that the flash memory has this erase before write requirement. So even though it is trying to read or write to a available page, it cannot overwrite in the same location, so it needs to pick some other location. Also, the granularity of erase and write are different, so if at all it needs to erase a block, right, it needs to move the existing pages in it to a new page, etc., new block, etc. The mapping can be done at the block level, page level, or it can be a mix of both. This is the primary task of FTL. The SSD controller also manages the wear leveling tasks because of the endurance issue that the flash memory has, because if we extensively use only a small portion of the cells, they will die out sooner than others. So the ideal case that we expect is all the locations should die out uniformly. Right? If we take one logical block here, 256 kilobyte, containing 64 4 kilobyte pages, we expect that after some time, the number of writes experienced or number of erasures experienced by the pages are more or less uniform. But in reality, because of the application's nature, it can be the case that couple of pages experienced a lot more erasures or writes when compared to others. What eventually would happen is here the page 0 and page 1 would die out when compared to the remaining 62 pages. Right? So to avoid this, the SSD controller does what's called wear leveling, wherein it will keep track of how many times a particular physical page has been written or erased, and whenever it needs to write, it will pick a new page, new physical page. So that's where the translation table is useful. So in the first instance, let's say there are green, blue, and red pages here mapped to physical pages 0, 1, 2, but after some time they have been mapped to pages 4 and 12 probably, and 17 or 18, right? So this mapping is done by the SSD controller, and to track this mapping, it needs an FTL. Now, because the pages are required to be erased before we can write, the SSD controller says, instead of erasing the entire block at this moment, I will write the incoming data in a new location and mark this particular page in the old location as invalid, right? And now when some threshold number of pages in a block become invalid, the garbage collector kicks in, and what it does is it moves all the valid pages in this block to a new block and frees up this and erases basically, right? So a quick example here, let's say each of these is a page, and together we call that as data block. There was a first write, the logical block address is 6, for example. So there was another write to the same location. So the first page becomes invalid and we write it to the second free page that is available. And let's say we had experienced 8 writes, and after the 8th write, this would be the status of this block. So the first 7 pages would be marked as invalid, and only the 8th page in this block will have valid data. Now, if you look at the overall capacity of this block, even though it is 8 physical pages, we cannot write anything in 7 pages. So at that time, the garbage collector looks for a spare block, moves this single block, a valid page, to the new block, right, and erases the previous block. Now, if we look at the overall capacity, we have 7 free pages in the block. So another example here, let's say we start with 10 pages of valid data, and again, let's say the processor has written those 10 pages, so we need to pick 10 new locations, and eventually, let's say the remaining locations in this particular block were also used. At this moment, the garbage collector will decide to move all the valid pages from block 1 to block 2 and erase block 1. And if we think about what would happen typically on a file deletion, right, when we just press delete or control or delete, assuming that it is permanently deleted, what typically happens is the OS directory structure is updated, but the physical page need not be erased immediately because of the issues of granularity at the SSD, right? So you can assume that the data is still residing on your SSD until and unless the garbage collector cleans it up, it will still remain there. So if you think a little further, you can potentially see as a security issue. So to support such operation, many of the SSDs will be equipped with the TRIM command. And what this TRIM command does is it will go and physically mark those pages as invalid. And once sufficient number of invalid pages are accumulated in a block, the garbage collector would kick in and erase it. And before that, it would move all the valid data to a new block. So to manage all this data movement, some extra space is needed. That's what we call as over provisioning. Now, in a typical SSD that you buy, even though they label it as 512 GB or so, we would be typically able to use only 480, 490 GB. The remaining 20, 30 GB is, you can assume, to be over provisioning. Right, and the SSD controller would use this for bad block management. Maybe the bad blocks can be termed because of the process variations or usage, etc. And it will also, all these extra blocks will help in wear leveling and garbage collection, and even to store the firmware, which is typically not visible to the user. And in general, these can be termed as the spare blocks, right? And if we another task that the SSD controller needs to look at is the read and program disturb, right? Whenever we want to read or write data to the flash cells, if you remember, we are going to apply a very high voltage. So this has potential to disturb the adjacent cells. Now this, if this rings a bell, this is similar to the row hammer issue that we are seeing in the DRAM. Right? So the SSD controller needs to carefully track in case some data has been corrupted. So what the SSD controller does is it will mark the adjacent cells, and frequently it needs to pick those cells and write them to a new location. So for that, it keeps account of how many reads and write programs are happening per page, and if they are reaching some predefined threshold, it will perform wear leveling, meaning that whatever row that is being frequently accessed will be remapped to a new physical location. And it will employ ECC also on the adjacent pages. I'll skip the write about for the sake of time. Like I said, the controller performs error checking and correction on all the data transfers that are happening between the host and the NAND flash. And there is a dedicated hardware for this, and it will be triggered by the SSD controller. In addition, with the usage, some of the blocks can die out. So the SSD controller needs to keep a track of those and update its garbage controller and FTL accordingly, right? So in addition, the SSDs, some of the high-end SSDs are equipped with the SMART feature, which is self-monitoring, analysis, and reporting technology, meaning that it will log all the activities that are happening within it, and when prompted by the host, it will supply all such data. And for security purposes, we have a encryption and decryption engine, dedicated engine on the SSD itself. And again, it is triggered by the SSD controller, wherein all the data of some particular file or a set of files, or maybe the entire SSD, can be encrypted. And this encryption and decryption will be done as upon prompt from the host, and typically AES 256-bit encryption is done. On the performance front, we have another level of cache, so to say, called the disk cache. So for simplicity, I have put the access time as the x-axis here, and various levels of memory that we see currently based on their access time. The fastest are the registers, which would be in picoseconds, followed by L1 cache, L2 cache, L3 cache, which would be a few nanoseconds, followed by DRAM, which would be typically 100 to 200 nanoseconds, followed by the current SSD that we are studying, which is in microseconds, hundreds of microseconds. And if you look at the typical magnetic disks, they are in milliseconds, very slow. And tapes, magnetic tapes are the slowest. Now, if you look at the gap between the DRAM and SSD, it is still high. So we have what's called a disk cache. Again, it is based on DRAM only. And to access any data on this disk cache, it would typically take a few hundreds of nanoseconds to a few microseconds. So the disk cache is predominantly DRAM based, and it can have some of the storage devices can have SRAM, and disk cache was even used in HDDs, right? In case of SSDs, disk cache can be used to improve the lifespan of the flash, because it can absorb as many writes as possible before eventually writing the data to the actual NAND flash cells, right? And on the performance front, a hit in the disk cache will save both time and power. The disk cache is primarily controlled by the SSD controller itself, and it will store the frequently used pages, the firmware, and any metadata that the host would need, or for the controller itself to maintain for proper functioning. And even the FTL would be part of the disk cache, right? Because the disk cache is primarily DRAM or SRAM based. Whenever there is a power loss, we expect all the data from the disk cache to be returned to the storage. So we have some extra battery backup, power backup. I'll skip in interest of time. And this is what we have overall, right? We have a lot of features that the SSD controller need to monitor and maintain, right? Both on performance front, on the reliability and simple the normal working front, and on the security we have a simple encryption and decryption engine. So with that, I will pause again for a couple of minutes for any questions. Okay, welcome back, everyone. We'll continue the session. So what we have seen so far is the notion that security aware designs are needed in general, and we were looking at the working of the NAND flash cells and how they are arranged to become the NAND dies, and how they are managed by the SSD controller. Right, in the remaining 15 to 20 minutes of this lecture, we will touch upon some of the security aspects in the SSD based storage devices. Right, so I'm going to state some of the threat models. Following that, we are going to look at two specific security issues, which are secure deletion and a ransomware attack. Okay, so what are the different possibilities of attacks in the SSD landscape, right? So one is the secure deletion itself, because every new data needs to be written in a new location, that meaning that we cannot overwrite the current location, right? And we mark the previous location as invalid, so on and so forth. If we delete the data at the user level, it would take some time for the actual deletion to happen at the device level. Now, in between this time frame, the file can still be retrieved from your SSD. So that's what would typically the storage or the memory restoration guys would typically look for, no? And the issue of untrustworthy supplier can be a case, because there are many different engines on the SSD controller that can typically sabotage the working of the SSD, right? It can decrease the lifespan, or it can mess up with the FTL layer itself, meaning the mapping can be changed so that different data is given to the user, so on and so forth. And the traditional read and program disturbances can be exploited much more aggressively, right? Like we have the row hammer attack at the DRAM, right? We can have a similar attack at the SSDs. What we are trying to do here is we are trying to read the same set of pages time and again, so that the adjacent pages or the cells in those pages get disturbed, and the value in them can potentially change. So this problem will be even more severe if you consider the 2-level and 3-level cells, because the value that is stored is dependent on the number of electrons that are trapped in the floating gate, right? Even a small change can flip the bits. Maybe the original data is a 110, but a few more electrons got dropped because of some adjacent voltage fluctuation because of the read operation. Then the value can become 100, right? And so potentially it affects the integrity of the data, right? There can be a very high level denial of service kind of attacks, wherein the different engines that are available on the SSD can be kept busy, either the encryption engine or the error correction. Each of these are working at page level granularity, right? 4 kilobyte or 8 kilobyte, and they take sufficient amount of time. Now, if there is an adversary program that is trying to engage these for its own use, the victim program will not be able to access the SSD immediately. It would be in the queue for a very, very long time. So it's not the total denial of service, but it is more like delay in the service, right? It would affect the performance of it. Also, if the aggressor program is deliberately writing a lot of data and not reusing it, right? What happens is the SSD blocks and SSD pages, their life can drop dramatically. Even though no matter how efficient ware leveling algorithms the SSD controller would use, right, to the program can still generate enough traffic, enough write traffic that the overall lifespan can drop. So that is another mode. And the another possibility is encrypt all the data itself. So we are going to study one specific implementation of this attack, which is ransomware. Right? Potentially, the attacker is encrypting all the data in your hard disk, and you are not able to access it. Now, this list is not an exhaustive list. There can be some a different type of attacks too, but these can be easily understood from whatever basics we have studied. Right? These attacks fall in or question the CIA properties or challenge the CIA properties or expectations from the user at different levels. Okay, now let's start with one of the popular security issue, which is the secure deletion aspect in SSDs. Now, let's say a program is writing a lot of data to the storage, right? And let's say there are multiple copies of the same address. Means the program is such that it is rewriting to the same location in its entirety of execution. Now, if there is one particular page that has been written, let's say 30 times, it means that there would be 30 invalid copies in the SSD, and there will be one another copy, the 31 copy, which would have the 31st copy, which would have the actual valid data. Now, how do we keep track of all these 30 invalid pages? Right? Now, if you ask why we need to keep a track of it, now the logical question is, when I as a user try to delete that particular file, right? The SSD is now expected to delete all the 31 copies of it. For that, it needs to keep track of the number of copies it has and the actual locations of all these copies, etc. Right? This is an issue, and if it is not tracking them well, it can end up not deleting those also. Now, for that, we would expect the garbage collector typically to kick in action, right? To clean up all these invalid pages. But the garbage collector would kick in only when there are certain or sufficient number of invalid pages in that particular block. Let's say a block has 64 pages, and we program the garbage collector to kick into action only when there are more than, let's say, 30 or 32 invalid pages. Now, if there is a potential chance that the remnants of our data are still remaining and the garbage collector did not kick in. Now, in that case, what can potentially happen is the attacker can try to access these pages which are invalid, right, and try to retrieve some of the data of the file that we actually deleted. Now, to handle such issues, there were a couple of techniques that were proposed, which are purging and ballooning. Right? These typically are proposed to force invoke the garbage collector. So why do I need to wait till I have, let's say, the 32 invalid pages? Why can't I do it before? What is the immediate effect of aggressive garbage collection is that the lifespan of the pages in this block will be reduced, because immediately the block will be erased, and also all the valid pages will be moved to the different block. So effectively it impacts the life. So we need to carefully tread this this decision on when to invoke the garbage collector, how frequently we have to invoke, etc. Right? So purging and ballooning are a couple of techniques that are proposed in this line, right? And there is another proposal which is true arrays. This particular proposal touches upon different layers, right from the user till the SSD layer. What it expects is the user marks each file with its importance. For example, there might be some files which are very, very important to the user. Let's say where we are storing some access informations or some other, it's even though it's not suggested, maybe there are passwords or credit card information, etc. in some files, and we decide that it's no longer required and we try to delete it, right? Such files can be marked by the user as important, and whenever he decides to delete them, an explicit action is taken up by the SSD controller immediately. Right? What it means is the SSD controller will kick into action the moment the file delete signal is given by the operating system, right? And irrespective of the status of the remaining the threshold that the garbage collector is looking for, it's going to trigger the erasure of the entire block. Another proposal was erasure crypto, right? It is a lightweight secure data deletion scheme. I put the paper here, right? What it does is it will encrypt all the files, and when the time comes, when the user prompts the deletion of some particular file, it will only go and delete those encryption keys. Now, what's the implication of that is, even though if we are able to retrieve some old invalid pages, we will not be able to read them because the decryption key is not available. So effectively, it makes the reading of these invalid pages useless. So that's how this smart proposal was brought up. So yeah, here are the three techniques that I was mentioning: purging, ballooning, and true arrays, and erasure crypto. Moving on to another example, which is ransomware. As the name says, it will hold you to ransom. But what is it trying to capture is all your data. So it is a malicious program. We can term it as a malware that will try to encrypt all your data, and it will demand a ransom for you. For you to get an unlock unlock the file, or probably it will give the decryption key for you to unlock it yourself. Right? So the encryption is so hard that without the encryption key, we will not be able to decrypt it. So this is how your system would look if there was a ransomware attack. This is just an example, right? So all you will see on your screen is a warning or a heads up saying that all your personal files are encrypted, and if you want to get the data, you pay so much amount, and there is an additional catch of time, etc. Right? This is very prominent nowadays, and I have put some news clippings for you to appreciate this point. Right here, you can see that FBI has seized roughly 2.3 million in cryptocurrency that was tied to ransomware attacks, meaning that the attack was performed and the attacker wanted some cryptocurrency, right? And the FBI was able to track it. And here is the another company which got hit by ransomware, right? Their offshore accounts were encrypted and they had to pay a huge amount, right? Another here is another story by company Ninja One, which came up saying that they have a new protection to the ransomware. And here is another news article on ransomware, wherein the power grid itself was attacked and the company was not able to track or generate any power because the data it was storing was encrypted, right? Another is an Australian government owned company itself was hit by ransomware attack, right? And then there is another discussion by a country level business leaders saying that ransomware is something that we need to equip ourselves with to handle it, right? And amidst all this, there are new ransomwares appearing every now and then. So if you look at the timestamp of all these news clippings, they are very, very recent, all in a span of past 48 hours, right? So the way ransomware infects the host system can be in multiple channels, right? It can be via phishing mails, or it can be any pen drive or any external device, right? It can be a spam, or it can be any malicious application that you would have downloaded, or any other vulnerabilities, etc., right? And typical phases of a ransomware attack are first the infection. It would first enter, the malware would enter into the system in one of the many channels that I have mentioned, right? Then it would communicate with the command and control server, which is actually maintained by the attacker, saying that this particular system is ready to be encrypted, etc. And it will ask for the encryption keys, and it will also share all the information of the target or the victim system, right? Then it will either overwrite or delete all the data of the user. And then comes the extortion, wherein the user is prompted to pay a ransom to get all his data back. Right? Now, this is not a new attack, and it has been there for the past few decades, but of late it has increased much more. Right? It started somewhere in 1989 itself, and you can see there were many variants of this. Right? WannaCry is one of the recent and most popular ransomware. Right? Rook was one more potential ransomware. And somebody nastily named the latest ransomware as Corona itself. So all the there is a very exhaustive article on this, a survey of on ransomware evolution, taxonomy, and defense solutions. Right. This is a very good paper. I would strongly suggest for you to go through to understand the origins of ransomware and how it has evolved and what are the defenses that have been built. Right. So typically, there are two broad approaches on handling the ransomware. One is detecting the ransomware as early as possible. And the second one is trying to recover the data after the ransomware attack has happened. So the recovery mechanisms, just for completeness, I have mentioned that it can be the file level, or maybe the encryption key itself, try to recover, or maybe recovery via some cloud services, etc. Right? On the detection mechanisms, there are quite a few different approaches. One popular thing that we do is keep a note of all the programs that are potential malwares and blacklist them so that they cannot be run or installed, etc. And one of the popular detection mechanism of late that has been picking interest is the machine learning based detection. Right? Now, if you are looking at the data recovery aspect, so the out of place update that we have seen as a drawback so far can be a potential help here. So even though the latest copy of the file has been encrypted and written somewhere, maybe its prior versions are available for us to read. So even though they have been marked as invalid, during the recovery process, we can try to read them and recover some part of the data, right? Of course, this is not totally efficient because we might not be able to recover the entire data, only bits and pieces of it. Now, there is an interesting approach named FlashGuard, right, which was trying to leverage such out of place update itself, right, and trying to recover as much data as possible. And when it comes to detection, like I said, machine learning based detection is catching a lot of traction. SSD Insider is one such approach, and Mimosa FTL is another approach where both of them used a machine learning model to try to see from the accesses that are coming to the SSD to make a informed guess that this can be a potential ransomware, right? If the trained model detects that it's a ransomware, then a corrective action needs to be taken up and the user can be informed that this is a potential ransomware, right? Now, another approach is key SSD. It is able to block access to the storage media once a ransomware is detected. And the one other popular technique is Project Almanac, a time-traveling solid-state drive, which is trying to propose that garbage collector needs a lot of sophisticated modifications to do data recovery better. Like I said, the ransomware attack is becoming more and more popular, and new versions of it are coming every day. The defensive mechanisms need to be adapted for the same. So one of my PhD scholar is specifically working on such defense mechanisms, primarily to detect a ransomware before it leads to any damage of the user data. The earlier we detect, the better. So with that, I would like to summarize the entire session. So for whatever reasons we pursued the betterment of hardware, it has left a lot more attacks possible, right? And the attackers are able to launch very fine-grained or pinpointed attacks because they have the knowledge of the underlying hardware. Now, as researchers or even working professionals who want to grow in the hardware security area, so here are some of the directions I would say that you should work on. First is know your hardware. Whatever module that you are picked, whether it's caches or main memory or network on chip or the processor itself, try to understand, get a complete understanding of it as much as possible. Now, once you gain the understanding, try to come up with all the threat models that are possible, right? If this can be from an exhaustive literature survey, or with your improved understanding of the hardware, you can come up with a threat model yourself, right? It's not that we are coming up with a threat model with a bad intention to launch an attack or steal some information, but it's rather saying that this is one of the potential things that were not explored till now, and this should be something we should be careful about, right? And we should study all the defensive mechanisms that are in place for the threat models that we studied, and like Dr. Srishandu said, it's very important to recreate the threat model in your working environment. Only then you can propose a new defensive mechanism. So with that, I conclude this lecture. Thank you for your attention, and I know that it's a New Year Eve and also the second half of Friday, but still I appreciate that all of you have joined and joined the session and listened to it. Right? I also wish you all a happy and prosperous New Year. Stay safe. I'm ready to take questions now. Thank you.
Okay. Thank you, Dr. Kalyan. And audience, if you have any question, please ask.
Sir, can you please tell me when will be the exam will start and where the link will be get?
So I would request all the participants to join the same session link. We are going to share it here. Okay.
Okay, in the chat box, right? Chat box.
Yes, yes. In the chat box, we will
Yeah,
share it.
yeah, sure.
When?
Thank you. Thank you.
At what time?
It's at 3:30. I
At 3.
posted a mail in, I think early in the morning, right? 3:30 to 4:30.
Yeah. Sure, sure. Thank you very much.
Yes. I'll stop the recording. Any
Yeah,
other
so
questions?
we can leave now, sir. We can wait for